Today we are going to talk about the insurance fractal. Let's start with a very simple equation in insurance. This is the one. We calculate the premium of a certain insurance policy for next year by taking the premium of this year and adding a percentage, a renewal percentage. If we do it by numbers, let's say this year you pay 100 euros and you get 5% on top of it when the renewal comes up, you will pay 105 euros next year. The year after you will pay 110, comma, dot for the UK people, 25 cents. And the year after 115 euros and 76 cents. And you can do this on, and in a graph it will look like this. This is all the mathematics I'm going to use in this video. So I'm going to rewrite the equation like mathematicians do. They're a bit lazy, right? They don't want to spell out what they're doing, so they shorten premium to the letter P. Next year becomes N plus 1. This year becomes N, and renewal percentage is the letter R. But it's exactly the same equation, and it's something that we call a dynamical system or a model. It models the evolution of the premium throughout time, and because of that letter, it's called dynamical because it changes over time. And a new concept, initial conditions. Here in the example, I started out with the P0, the premium this year for 100 euros, and I took a renewal percentage of 5%. Those are called initial conditions. So now you've learned some new, some new labels that mathematicians use: dynamical systems, initial values. And we want to evaluate the behavior of this dynamical system. Why? Because we learned that if the policy goes beyond 500 euros, people will cancel their policy. We will lose the customers, and we don't want that. We want to keep them, and in this case we want to keep them for at least 10 years. So we are very curious to find out in which year will people cancel their policy for any combination of initial conditions, for any starting point for the current premium and in combination with a renewal percentage. So let's do this. Let's do the numbers. I'm going to repeat the evaluation. Here is a table. Don't be worried. Keep breathing. Relax. I'm going to walk you through it. On top, I picked some values that we could use for the initial condition number 1, which is the current premium this year, P0. I started out with 50, ended with 300. Here is initial condition number 2, the renewal percentage. I started out with 5, ended with 25, and I added steps of 5%. And again, I want to know in which year are we going to lose our customers. And that's where the numbers come in. If you look at the top left, 48, this means if you start out with a policy that's 50 euros, the column, and you apply 5% each year, the row, then in year 48, the premium will go beyond 500 and it will be cancelled. Let's look at this number, number 10. First, I want to go back to the year number 9. If we are now in the column where I picked a combination of a starting premium of 200 euros and a renewal percentage of 10% each year. And if you want to do the math, and you should all be familiar with this simple equation, you take the base premium 200, you multiply it by 1.1 to the power 9 for year number 9, and you will see we get something which is still below 500 euros. But the next year, in year number 10, it will go beyond, and this customer will cancel his policy in year number 10. And that's why I colored it orange, not happy. If it happens after year number 10, I colored it green, happy. Very simple, right? So again, the table, I took out the colors because I want to use a different coloring scheme. It's arbitrary, but now I want to do it like this. If we lose the customer in year number 1, really not happy, deep red. If we lose the customer in year number 10, not happy, but not so sad as in year 1. So I made this yellow, and in between there's some gradient. And if we lose the customer after 10 years, we're happy, and instead of green, I use black. And if we use this color scheme, then we get this image. Let me take myself out of the picture. Where do I need to go? I need to go to this one. Yes, there we are. Okay, so this is it. This is the fractal, the insurance fractal. It does not have lots of detail and resolution, so let's fix that first. Where is my cursor? There I am. So here it is. I can put myself back into the screen, I think. Yes, there I am. So here we still same fractal, right? The insurance fractal, ranging from 50 euros to 300 euros for the base premium, and ranging from 5% to 25% for the renewal percentage. And for each combination, we calculated the year in which the policy gets cancelled, and we use the color scheme as discussed before. So now you see a little bit more, less graininess, and you can add more and more detail. I'm going to repeat myself a lot because basically we're ready, but I just want you to fully understand. Again, I need to be out of the way like this. So we have the dynamical system, initial conditions, an evaluation scheme, and a color table. And that's all there is to it. I'm going to repeat it again and again, and I'm going to put myself back into the screen again. Here I am, yes. So yeah, let me take me one step back. I added the word constants, but sometimes you run into models that also have constants in them. In this case, we don't. Both P0 and R are initial conditions that we are going to vary across the fractal. And when we draw the fractal, well, we first decide how many iterations are we going to do, in this case 10. We paint all pixels black by choice, and then we say if somewhere between iteration number 1 and 10, the threshold of 500 euros is surpassed, then we start coloring in, and we will use this color scheme. If it happens really quickly, deep red. If it happens a little bit later, more yellow. And if it happens beyond the iteration list, like from N is 11 onwards, black. And this is what we got. Okay. Now, are you ready to see the real deal? Because here's the real deal. This is another dynamical system, and you do not have to understand anything of it, only that it has 4 things in them: X, Y, CX, CY. That's it. That's all there is to it. This model pops up in weather predictions, but you can forget about it. It's just a model, a dynamical model. Here we have initial conditions CX and CY. Those two we are going to vary across the fractal. And the range for CX is usually -2 up to +1, and for CY -1.5 all the way up to 1.5. And when we start calculating, we need to put in X0 and Y0 as a starting position. Those will always be 0 in this case. Again, similar, an evaluation scheme. We will do this for 350 iterations. We color all pixels black, and if somewhere during the iterations x squared plus y squared goes across a threshold 4, we start coloring in, and we will use the exact same coloring scheme as we use for the insurance fractal. Hold on to your seat if you've never ever seen an actual fractal. This is what it will look like. Boom! It's called the Mandelbrot set, the most famous fractal of them all, the Eiffel Tower of fractals. Very different from the insurance fractal, right? But there's more different. 1. If we zoom in on the insurance fractal, we might see something like this. No matter how much resolution you put in there, no matter how many pixels you put in there, no matter how far you zoom in, you will see a perfect sharp line between the black and the yellow. No hidden structures, no nice color schemes, etc. This is it. You can zoom in, zoom in, zoom in, but it will be pretty boring, I'm afraid. If you do so with the Mandelbrot set, you will not be bored. Here I zoomed in on a tiny piece in the red of the Mandelbrot set, and again you see lots of structure. You see pixels that are being colored red, which says they are escaping the threshold of 4 pretty quickly during the iterations. And next to them there are yellow and black ones that either escape slowly, only after 350 iterations, then it will be fully yellow, or it will not escape at all, and then it will be black. And just to give you a feel, the entire range of C-axis and C-Ys in this zoomed in portion is 0.00001. So the difference between 2 pixels in this picture is even less. It's like 0.000001 or maybe 0001. So this dynamical system is extremely sensitive to the choice for the initial conditions, the Cx and the Cy. If you change Cx or Cy just by a tiny fraction, the color will tell you that it might behave completely different. It will escape, it will not escape, it will escape quickly, it will escape slowly, and that's what you get from the colors. So this is it. Let's see. So, is the insurance fractal a fractal? No, it's not. Why? Because one of the key properties of fractals is that when you zoom in, you keep seeing new structures and color schemes popping up, like I just showed in the zooming on the Mandelbrot. If you zoom in on the insurance fractal, you will just see a very sharp line between the black and the yellow. So unfortunately, the insurance fractal isn't a fractal, but I hope it helped you to fully understand the analogy with the Mandelbrot fractal. Can you change the color schemes? Of course, as I said before, it was completely arbitrary. Well, not so arbitrary. I use color schemes that are regularly being used, but here I used different color schemes for portions of the Mandelbrot set. How did I do this? I'm using Chaos. It's open source, easy to install software, free of use, no account. It runs perfectly, and you can just say, give me a random color table. Oh no, I don't like one. Give me another. And that's where you end up with these nice looking pictures. For all the insurance people, I hope you fully got the concept of fractal, and if you did watch my other videos on fractals, go revisit them, and I'm sure everything will be crystal clear. Thank you for watching.